So in my last lecture we were talking about the routing algorithms, and we looked on to the basic of routing algorithms, and we also named which all routing algorithms we are going to cover. So let us recap that lecture in a nutshell, and then we move forward for today's agenda. So when we say about routing, it is one of the major kind of we can say work or the task of the network layer. And in terms of routing, when we are looking for the shortest path routing. That means the algorithms which help us to find the shortest path between a sender and a receiver for routing the data packets through the network. Now the shortest path can be in terms of shortest distance, it could be minimum cost, it could be minimum delay or something of that sort. All those metrics we have looked into. Now the shortest path algorithm is basically kind of used by building a graph or the subnet containing routers and nodes and edges as the communication lines connecting those nodes. So one of the parameters we looked on to was the hop count, which is the actually the number of the routers or which are covered onto that particular link, the number that indicates how many routers are covered. And if the hop count is, let us say, 6 or any other number, so that means 6 routers per 6 routers or nodes are being covered onto that path, and obviously edges are there in order to connect them. Another metric which we already looked in is geographical distance, which is something in kilometers or whatever. So we can find the label and label on the arc and write that as a function of maybe the distance, it could be average traffic, it could be the bandwidth, communication cost, delay and something of that sort. So all these can be kind of metrics. So it could be, as I have told you, the mean delay or something of that sort. So the graph labeling, whenever we are talking about the shortest path, is actually the fastest path rather than the path with the fewest edges or kilometers, if we are talking about some other metrics like mean delay. Now we can change this weighing function as and when required, depending upon which criteria we are using. Now this criteria can be a single criteria or it could be a combination of criteria also. Now what all common shortest path algorithms are available which can be used for these routing decisions? So the common ones are Dijkstra's algorithm, Bellman-Ford algorithm, then the third comes as the Flad-Warshall algorithm, and we are going to look into all these 3 algorithms, but these algorithms are not necessarily the only ones which are available. So what I am trying to say is the list is not exhaustive. Let us move on to the first shortest path algorithm, Dijkstra's algorithm. Although these algorithms which are shortest path algorithms fall into the subject of we can say data structure more appropriately, but as we are talking about the routing and the shortest path algorithms here, that it makes a perfect sense to discuss these algorithms here as well. So Dijkstra algorithm, basically a greedy algorithm which is used to find the minimum distance between a node and all other nodes in a given graph. Now let us say that node is nothing but a router, the graph is depicting the whole network. Now it can use any metric, the weight of edge can be the metric like the distance between the nodes, and in order to find the minimum distance node we are going to use this algorithm. Now how this algorithm is going to take place in a step by step manner, let us see. So we need to initialize all the nodes. For this we will be setting the distance of source to 0 and all others to infinity, and that makes a sense because the distance of source from source is 0, and to all other, as we have not calculated yet, we are going to initialize the distance from source to all others as infinity. We are going to mark all the nodes as unvisited, and as we have not determined the predecessors of the nodes, we are going to kind of name them null in the initial phase. Now, among all the unvisited nodes, we are going to choose the smallest one, the one with the smallest current distance, and then we will kind of update the neighbors for each unvisited neighbor n of the current node. So, from source we will be looking into whichever is the smallest current distance, we will go on to that particular node, we will select the current node, and then after selecting the current node, for each unvisited neighbor n of the current node, we are going to compute the distance, which is the new distance is already the current distance, which is kind of already being covered, plus the kind of weight of the edge from the current to the end. So, for example, let us say we have started from 0 and now we are at, let us say, 1, and now from 1 to 2 we need to go. So, 0 is our source. So, from 0 to 1, let us say 10 units of the metric we have kind of we can say we incurred as an expense. So, that 10 plus the weight of the edge from 1 to 2 is, let us say, 5, then it is going to be 10 plus 5, 15. So, the new distance between the source and the next one is going to be 15. If new distance is less than the distance of n, then we need to update the distance of n as the new distance, and also in this in the similar manner we are going to update the predecessor of n, which is going to be the current one. So, we need to see that which particular path is going to be beneficial, whether which is covering the current one, or maybe kind of it is the direct path or not covering the current one from the source to the next one. And we also need to mark the current node as visited, so that we should not fall into the loop, and this is what we are going to kind of update if there are unvisited nodes still exist. So, by the time you have your unvisited nodes in the queue or in the whatever data structure you are going to use, in the data structure, we are going to perform this step of updating the predecessors if required and updating the distance, updating the new distance. Now, distance is going to contain the shortest path, and predecessors are maintained in order to be used to reconstruct the current path. So, in order to understand this whole algorithm, let us take an example graph here. So, here we have the nodes starting from 0, 1, 2, 3, 4, 5, 6. So, total 7 nodes in the graph, and there is an kind of label, there is an weight of the edge connecting each and every wherever the connections are available. So, now let us say we are going to begin with 0 as our source node. So, taking a start from the initial node, which is the 0. Now, here we can see that the distance, if you can see on the right side as a table, what are the unvisited nodes left. So, 0 is now visited. Now, 1, 2, 3, 4, 5, 6 are unvisited, and the distance of 0 from 0 is nothing, which is 0. So, the distance from source to source is 0, and for 1, 2, 3, 4, 5, 6 we have not calculated yet, or we have not visited them yet. So, we are going to kind of mention them as infinity. So, this was actually the initialization step of the our algorithm. Moving forward, if we look into from 0 where what all the paths are available. So, from 0 we can go to 1, from 0 we can also go to 2, and in the similar manner we need to kind of update the distance. So, from 0 if we take 1, there is an expense of 2 units, and from 1 if we go to 3 there is an expense of 5 units. So, if you can see, so from 0 to 1 it is 2 units, then from 0 to if you can see 2 it is 6 unit, which is already labeled on the screen. But now there are 2 paths to reach to 3, whether we can we can use 2 as the intermediate node or we can use 1 as the intermediate node. Now see, if we are going to use 2 as the intermediate node in order to reach to 3, the total sum of the expenses or total sum of the weight of the edges is going to be more than in this case, and if we are going to use 1 as the intermediate router, it is just kind of 7. So, we have updated 7 as the distance to be covered starting from our the source, which is the 0. So, from 0 to 1 it is 2 units, from 0 to 2 it is 6 unit because no other path is existing, or we can say it is a longer one, and from 0 to 3 rather than going by taking intermediate as the second one, we are taking intermediate as the first one because that is the shortest path. And in this way your Dijkstra algorithm is going to kind of update this path for each and every node. Now looking on to 4, if you can see, we can use the path 0, 2, 3, 4, or we can use 0, 1, 3, 4. Now here comes the principle of optimality in the practice. If in order to reach to 3 we have not used 2, going from 3 to 4 we cannot use 2 because that is not going to result into the optimal path. And here is what the principle of optimality is kind of we can say it is saying the same thing in a manner. Moving forward with this particular graph, if we can see now we mark that node as visited, which is 0 was already visited, then we have marked 2 as visited. So, in order to go to 2 we need to kind of incur an expense of 6. In order to reach 1 we need to incur an expense of 2. For 3 it is going to be 7. Now moving forward from 3 either to 4 or to 5 we need to see. So, from 3 to 4 till 3 we have an expense of 7. So, from 3 to 4 10 plus 7 again 17, and from 3 to 5 so 7 plus 15 which is nothing but 22 because that is the shortest path which is available here. Moving further, if we need to go to 6, so till 4 we have 17, and from 4 to 6 so 17 plus 2 more which is 19. If we opt for the path through 5, this is going to give us kind of a higher expense because 5 is already at 22. So, 22 plus kind of 6 more will give us 28. So, it is a better idea to reach to the node 6 using the path with the intermediate router as the fourth one. So, even if we want to reach to 6 from 0, we will be taking this path. So, from 0 to 1, 1 to 3, then 3 to 4, and then 4 to 6, and so on and so forth. So, this is kind of what technical term we can use for here is actually normalizing the distance, and we also need to keep a track of that this we should not fall in a loop or we should not fall in a cycle, and in because of this we are going to keep a track of the visited node. So, this was Dijkstra's algorithm, which is kind of an greedy algorithm we can say, and it keeps on looking for the shortest distance for every hop we can say, or for every node. So, this was the first algorithm. Moving forward, the next algorithm which is coming up is Bellman-Ford algorithm. Again, it helps us to find a shortest path between a source vertex and any other vertex in the given graph. So, here is a difference. When we say Dijkstra's algorithm is to find single source all destinations, because in the previous algorithm, if we look into the table, distance of all the nodes starting from 0 as the smallest path is being, kind of we can say calculated, is being determined. But here if we talk about Bellman-Ford, originally, or in a naive manner, it is used to find the shortest path between a source vertex and any other vertex in the given graph. It can be used in weighted as well as non-unweighted graphs both. Slower than as compared to Dijkstra's algorithm, but the benefit here is that we can use negative edge weights also. So, if the edge weights are negative, then Dijkstra's algorithm is going to fail, while your Bellman-Ford algorithm is going to kind of we can say crack that, because it is having one we can say extra kind of iteration in order to identify the presence of negative edge negative edge cycles. So, negative edges are perfectly okay if they are available in the graph, but the negative edges cycles it is not able to handle. Now, Bellman-Ford, when we say we initialize all the vertices in a distance array as infinity, we are going to pick a random vertex 0 and we are going to assign that the distance array, which is distance of 0, is 0, and we keep on iteratively updating the minimum distance to each node, let us say V, by comparing it with the sum of the distance from the source node and the edge weight, and this is going to be done kind of n minus 1 times, and in order to identify the presence of negative edge cycles, one more cycle or one more iteration, which is the nth time. So, and all this can be done with the help of what we can say is edge relaxation. So, edge relaxation says, so whenever we are going to find an updated shorter path, we are going to relax that edge, or we are going to in a simple manner we can say we are going to update the distances. And if a negative we are saying that the negative cycle is will not be handled by this Bellman-Ford, that a negative cycle is going to exist if for any edge the sum of distance from the source node and the edge weight is less than the current distance to the largest node. So, this is we can say is the manner in which the negative existence of negative cycles is being determined in this Bellman-Ford algorithm, and it indicates the absence or maybe presence of negative cycles if that particular kind of that particular constraint of the sum of the distance from source node and the edge weight is less than the current node to the largest node satisfies. Then in that situation we can determine the absence of negative edge, absence or presence of negative edge weight cycles, not the negative edge weights. So, here if you can see on the it is available on the screen, here is a graph. Please kind of we can say observe this graph, and this graph is having some of the edge weights which are negative. Now, if you can see, there is an edge from A to B, it is having a edge weight of 5, from B to D it is 2, from B to C it is 1, C to E is 1, then E to D is -1, D to F is 2, and F to E is -3. Now, if you can see the cycle between D, F and E, there is a negative weight cycle, because 2 plus -3 is -1, and then -1 and -1 is going to give you minus 2. So, that means this cycle or the kind of sum of the all the way edges of this particular cycle is going to result in a negative weight. So, that is why this is what we call is a negative weight cycle. Now, Bellman-Ford is efficient enough to detect a negative cycle in a graph with the kind of steps which we have just seen. Let us see them. So, we need to initialize the distance array first, and we are taking A as the source. Now, please observe the distance array. Now, in this distance array you can say the distance of A from A is 0, and to all other nodes the distance of B from A, the distance of C from A is presently it is infinity, because it is in the initialization phase, and that is what your distance array is showing also. Now, we need to update this distance array with the help of relaxation of edges, and the formula for relaxation of edges is given here. So, now in the kind of we can say in the step of relaxation we can say from in going from A to B the distance will be incurred as 5, and going from B to C it is 1, but presently it is as we are going to take it in a node by node manner. So, presently our B or the edge which is A to B is kind of we can say C, and the distance array is just updated only for the node B, and in this way we will be kind of taking it for all other nodes. So, for example, let us say we have a node E. So, now we need to see that whether the distance or whether the path from A to B, then from B to D, then from D to E, then there is no path. So, in order to go to E, we need to take A to B, B to C, and then C to E. Whatever is the sum is, which is 5 plus 1 and then 1 is going to be, which is 7, is going to be kind of the value under the node E in the distance array, and here we kind of keep on relaxing the edges if we can do them. Now, in the second kind of iteration of the relaxation of edges, we started from B. Now, from B there are two paths, one is going to D and another one is going to C. So, for C we have incurred 5 plus 1 which is 6, and for D we have incurred 5 plus 2 which is 7, and hence we have updated the distance array. In the third relaxation of edges, now we need to move forward from kind of C and D also. So, what is happening? So, from D we end up to the F, and from C we end up onto the E, because these are the paths which are kind of available, and hence we have kind of relaxed the edges. But if we look into kind of the measure of E presently, so we have A to B is 5, B to C is 1, and then from C to E is again 1. So, 5 plus 1 makes 7. But here if we take the path from R, it is going to be kind of 9, and then 9 minus 3 it is going to be 6. So, a shorter path is available. Then taking this path, if we move on to the D, so E is at 6 and 6 minus 1 we will end up with 5 onto D. So, this kind of kind of loop if we can look into, after third relaxation of edges, if we come to the fourth relaxation of edge, E is now 6, while in the previous one the E was at 7. So, here kind of, and then D has again decreased from 7 to 6. So, in this way if we keep on moving, and here in among these nodes which are D, E and F, it is actually a negative weight cycle. So, it will keep on decreasing every time we move on to D and E, and then finally what will be the outcome of the Bellman-Ford algorithm to be implemented on these kinds of graphs is that this graph contains a negative cycle in the path from node D to node F and then to node E. So, this is going to be our final outcome, because you keep on decreasing the edge weights, you keep on relaxing the edges, and because of the negative weight cycles you essentially fall into a loop, and that is where we need to stop that, saying that the graph, the presence of a negative cycle has been detected. Moving further, the another algorithm or the last algorithm which we listed was the Floyd-Warshall. It is again an algorithm which is used to find shortest path between any two nodes in a given graph, and it keeps a matrix of distances between each pair of vertices, and it will continue iterating the matrix until it reaches at the shortest path. So, we are going to take the data about the graph in the form of a matrix, and taking all the vertices as intermediate vertex, we need to update the final matrix. One thing which is worth noting down here, that it includes at a time that we pick one vertex, update the shortest path which includes the chosen vertex as an in between point along the path. So, when we select a vertex, let us say k, almost like the middle of the path, in the previous calculations we have already taken all the vertices from 0 to 1 to k minus 1 as potential middle points. So, in order to kind of going from 0 to 5, we will take if we are going to able to take 1 as the middle vertex, 2 as the middle vertex, 3 as the middle vertex and 4 as the middle vertex also. And taking this information, the whole kind of matrix is going to be updated. So, in order to kind of look it in a brief manner, let us look at this as an example graph. So, here we have an example graph which is being shown on the screen, and it is having 5 nodes A, B, C, D, E, and kind of one particular node can be accessed or can be reached using multiple paths. So, from C to B, if we want to go, there is a direct path, then there is a path which is going from taking A as an intermediate one, then it is also having a path which is taking D and E, then A as the intermediate one. So, all these information is to be updated in the matrix. Let us see how. So, we have initialized the distance matrix using this input graph, and all the direct edges which are there are being kind of filled in. So, from A to B it is 4, from A to D it is 5, from B to C it is 1, then from B to E it is 6, and we kind of have used this matrix. Now, what do we need to do? We need to update this matrix if we take node A as the intermediate node. Are we able to kind of decrease the path? Then we are going to update it, and this will be done for all the nodes. So, this is the figure which is showing using node A as the intermediate step, then we have this as using node B as the intermediate step, and then finally we will be having node C, node D and node E as the intermediate kind of nodes or as the intermediate steps. So, in this lecture we looked on to the 3 routing algorithms which we discussed were Dijkstra algorithm, then Bellman-Ford algorithm which was there for negative edges and for the detection of negative weight cycles, and the Floyd-Warshall algorithm. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.